All right, I'm Jon Prier. I'm from ODOT, Ohio DOT. We're talking about bioretention. So I'm the kind of the post-construction BMP guy, one of them at Ohio DOT. So show of hands, who's put a bioretention cell in a set of plans before? So I can see what we're dealing with. All right, so a decent amount of people. So none of this is groundbreaking. This is just how ODOT's been using bioretention cells recently on a few projects, and will continue in the future, and how we've solved some of our common problems associated with right-of-way and safety and construction. The big problem is why people are scared of bioretention cells, right? Because they're easy to screw up, right? And their contractors aren't used to building them. So, ta-da, that's a bioretention cell. Obviously, it's a beautiful bioretention cell right in the middle of I-70. You might have driven by it at some point on your way here. Cars are going by 70 miles an hour. It's right in the median. It's safe. It looks ugly, right? It's full of weeds, and those weeds are working beautifully for stormwater. There's no problem there. So we're going to talk about that case study a lot, because for bioretention cells for stormwater, I don't care a whole lot about right now about not having weeds in my bioretention cell. I care about the stormwater being treated and doing what it's supposed to do. So we're going to come back to that bioretention cell a few times, but since it's 2018, I'm going to use some state-of-the-art technology and do PowerPoint animations from like 1995 to show you how our bioretention cells are supposed to work. So people know what bioretention cells are. Sometimes they filter quickly, sometimes they go slowly. This is how ours are supposed to work. So that obviously is a ditch next to a road, as you would draw in PowerPoints. And there's grass growing in the ditch, right? And then there's a cloud, and clouds produce rain, and rain looks like that in PowerPoint. And when rain falls on a road in PowerPoint, it produces orange water because it's dirty water, right? Because I haven't been through our BMP yet when it's going to turn blue. So for bioretention cells, it goes through some level of pretreatment, some grass that we have, and then goes into that ditch. And for our bioretention cells in ditches, we put some kind of water quality dike on the downstream end and pond up above. And then the idea is the water's supposed to go down, right? Hopefully you can see. Oh, sorry, I have happy little sediment particles coming in. That's pollution, because in PowerPoint, pollution are orange dots. Those go into the pool of water, and then water eventually goes down through the engineered soil, and then into some filter layer, and then into some underdrain layer, 57s with a perforated underdrain, and then happy, clean blue water comes out the other side, right? That's what a bioretention cell is. Nothing magic. I'm not doing phytoremediation or any fancy chemical thing. It's a soil sponge cleaning up the water, knocking the pollution down, and allowing time for some evaporation and things like that to happen, okay? Nothing magic, simple engineering. All right, so that's what we're going to be looking at. So in Ohio at ODOT, we have two types of bioretention cells that we have kind of sample CAD plans pulled up for. A simple flat site, and this is the most engineering type bioretention cell you could have, right? It's an ugly rectangle. You can get your area figured out. I don't want to talk about flat sites that much. That's the typical one with a catch basin in the middle. I want to talk about sloped sites in a ditch, because that was my presentation, right? If you can fit a ditch, you can fit a bioretention cell. How exciting. So this is a ditch, and we're going to dig a bioretention cell in the middle of it. It's very simple. I don't have a pointer, but you can see the plan view up top. It's just you're basically digging a pipe trench, and instead of putting a pipe in, you're putting this bioretention cross section in, where you got underdrain, some filter media, some more filter media, and then that engineered soil and some other things. So we're going to talk about sloped bioretention here for most time, bioretention in a ditch, and we're going to focus on what our design criteria are, and then how we keep from messing it up, right? How we keep from screwing it up. So in Ohio, we have really simplified bioretention cell sizing such that our regulators have agreed for ODOT just to allow it to be 5% of the impervious area. So as long as the area of our bioretention cell is 5% of the impervious area, we're set. No water quality volume calculation, no water quality drawdown calculations, nothing fancy like that. We do have a specific soil mix that we choose to get the water to percolate through the soil kind of slowly. So we're shooting for that 2 to 4 inches per hour. None of that's 10, 50, 100 inches per hour. We would call that media filtration, not bioretention. So when we say bioretention, we're trying to slow down a bunch of water and hold it back a little bit. Across the nation, there are lots of different ways people size bioretention. There's the one Maryland came up with 20 years ago. But all those equations are kind of fudged to get the answer to be somewhere between 4 to 8% of the impervious area. No matter where you are, that's always what it comes out to. So we kind of took out all those saturated hydraulic conductivity numbers that you were forced to make too low to get your bioretention cell to be 5%, and just said 5%, go from there. So nice and simple. So 5% of the tributary is huge, right? From a BMP standpoint, that's a big tributary. Detention basins are 1% to 2% rule of thumb of their tributary area. So 5% is way too big, so that's annoying. But we have roads, we have linear applications. So in a linear application, 5% of your cross-section is really much more doable than 5% of your big site where you have to put a big basin at the downstream end. So let's take a look at what this looks like. Ohio's kind of weird. Our regulator makes ODOT treat all of our right-of-way as impervious for BMPs, which you don't really need to know that. But the key is we're gonna be extra conservative here, and we're gonna say from crown of the road, that's a super elevated road, and it's just a 2-lane road, to the edge of our right-of-way where that fence is, we're gonna consider that impervious, and that is 40 feet. Okay, so anyone know quickly what 5% of 40 feet is? 2. All right, we got some engineers. All right, so 2 feet. So 2 feet looks like that in Google Earth in this picture I took. So 2 feet is not very much. So the point of this is that we can fit this cross section into a lot of ditches as long as we can get it out somehow. So this cross section is really simple. It's again, you're just digging a trench, however wide you need to be. So we're going to make this 2 feet wide, and we're going to fill it up with 12 inches of 57s, and then 3 inches of 78s, clean 78s, washed 78s. 3 inches of clean fine aggregate, clean sand, so washed sand, and then 30 inches or 2.5 feet of our bioretention mix, which is a pretty simple mix. And we're going to build it up a little bit because it's going to come down a little bit. But that's all we're going to do. We're not going to use any filter fabric. We're just going to put in those 4 layers with an underdrain in it. So it's not wildly expensive. So let's just see what this looks like in a ditch to give you confidence that this might fit in a lot of our ditches, right? So if I imagine what that catch basin looks like in 3D and PowerPoint here, I can kind of have my little pipe trench I dug out, and I can fill the bottom 12 inches with those 57s. The next 6 inches is those 78s and that sand, which we use that 6 inches of filter media instead of a filter fabric because filter fabric clogs and we don't like those. So that's why we use this filter media section. And then we put the good stuff, the bioretention soil that's doing all the work at the top 2.5 feet, 30 inches. And we put a little water quality dike there. And it looks kind of funky, and I'm going to talk about that in a second because that was one of the hurdles we had to get over. And we let water pond behind it, and water goes down through the bioretention cell. Everyone's happy. It's great. Okay? So that's for area of the bioretention cell, that's very simple, right? 5% of the tributary area, which a lot of times on a linear application can look like 5% of your cross-section area, which fits in a lot of right-of-ways. So the next question is the reason this works, one of the reasons this works is because we're ponding up water, forcing water down through the bioretention cell, not letting it go down the ditch and not get treated. So we need some way to hold back that water safely, okay? So we have this 10-inch earth dike. So no one likes telling a contractor to build a 10-inch dike. That's annoying, but we did anyway. And we're putting what we call tied concrete block mat, so those concrete squares that are on top of the mesh, right? On top of that, which is 2.5 inches deep, depending on who you're getting it from. So that gives you a depth of about 12 inches. So in Ohio, we are allowed 12 inches of inundation in the clear zone next to the road, right? So this is where we are. We're fitting this. And in Ohio, for safety grading, we have to have no steeper than 6-to-1 slopes in the clear zone, all right? So we built a dike that's 12 to 14 feet wide, big, and 1 foot high, or 10 inches high, and then covered with a tied concrete mat to make it 12 inches high, which is simple, right? It's not that complicated. It's big. It ends up being like a 14 by 14 foot section out of your ditch, but it's not that expensive. We're talking about dirt and some mat, and it's supposed to be safe within the clear zone. And when you compare it to a lot of the slopes of our catch basins that we have in the clear zone anyway, it is relatively safe. It's probably not as safe as having nothing there, but we got to hold water back somehow to get water to go where we want it to get credit for treatment. So this is something we can put in the clear zone next to traveling traffic without having to put up barrier protection, which is a big, big plus for Ohio, right? So We keep the slope 6-to-1 or flatter, and we keep the maximum ponding to less than 12 inches. And in our bioretention cells, we don't like more than 12 inches of ponding anyway. So we had to do some talking with Ohio EPA about this because we can't store, it's a sloped bioretention cell. So if you put a level pond, you have 12 inches of ponding on this end and zero ponding on that end. So it's not perfect, but at 5% of the impervious tributary area, we think we're getting we're trying to treat about 90% of the average annual runoff. We think we're getting that to go down through the bioretention cell. So, and Ohio EPA, our regulator, agrees with that. So in the field, this beautifully looks like this, right? It looks like nothing almost. So this is that same one of the 7 bioretention cells we have in the middle I-70. And you can see the little tied concrete mat berm, which was just a little berm that the contractor did not like doing. We had to have him get out there twice, but then it wasn't that big of a deal. And you put that mat on top of it, and then when water ponds in the ditch, it backs up to 12 inches of ponding. So in practice, it looks kind of like this, if you look at it on a real condensed scale. So we end up putting one of these dikes at every 1 foot of fall. That's our requirement to push water down, okay? So that is annoying if I have a 3-4% longitudinal slope ditch, then I'm putting one of these every 25 feet, right? And they're 14 feet long. I can't do that. So I'm not talking about, once you get to about 3 feet or steeper, Ohio would have trouble with these. But that ditch on 70 is 0.3%, or we're putting one about every 300 feet. So that's great. And at a 1% slope, you're putting one every 100 feet, and that's not really that onerous. You end up splitting your cells into a bunch of mini cells for every 1 foot of fall. So it's pretty straightforward, not too complicated. People can get the idea of that. You are still putting it in a ditch. So I will say, even though we're using it as a BMP and we want a lot of the water to go down, you do still have to size your ditch to convey water. So don't put in one of these 12-inch dikes and then be surprised when you flood your interstate foot. You still obviously have to make sure your freeboard's low enough, considering that. So we talked about area of the bioretention cell bed area. We talked about the water quality weir, making sure that's safe and holds back water appropriately, and we have enough of those. And then pretreatment. Pretreatment's the big thing, so that's what people are scared about for bioretention cells, is them clogging up and failing, because everyone likes bioretention cells, but it's really easy to screw them up, and we've all seen those horror stories of ones that look, completely silted in and don't work at all. So you need pretreatment. In a linear application, we think that 5 feet of grass is enough pretreatment to protect these bioretention cells. So most of our ditches have 5 feet of grass, which is why the title was, if you can fit a ditch, you can fit bioretention cells. So when you do have concentrated flow, you have to do something a little more annoying. You have to make it go through at least some length of grass ditch to knock the sediment down, or some actual forebay that's sized for 10% of the water quality volume. But you need basically, on most of our linear applications, we need at least 5 feet of grass, which we have in a lot of places. That's the key, is we have a lot of space for this bioretention cell within our right-of-way without buying more right-of-way. So at our site before, that little road, we had 8 feet there, which is plenty. And that is going to do a pretty good job knocking the sediment down, as long as it stays sheet flow before it gets to our bioretention cell. All right, the last part for the design is the hydraulic drop. So we all know sometimes you have steep areas, sometimes you have shallow areas. These bioretention cells, we're sending water down through a sandy soil to an underdrain, right? And in Ohio, none of our soils are good, have high in situ hydraulic conductivity, so we always have to have an underdrain. If you're lucky enough to have sandy soil somewhere, you have all kinds of options, you're fine, you don't need this presentation. For all the rest of us who have clay soils, we need to have an underdrain there, and the normal drop for that is it's a 4-foot section, so the underdrain sits up 3 inches, so it's 45 inches from the ground surface down to that. But we're allowed an internal water storage, which is something environmentalists, people who like the environment, like I do, we like internal water storage because it means more that water stays there, has a lot of time to infiltrate. The pure civil guys like it because I only need 2 feet of drop to get out, right? So if I have any structure, any catch basin nearby in my ditch, I can get my underdrain outlet to that because all I need is 24 inches. In Ohio, we don't have any catch basins less than 30 inches, right? So I can core into any existing catch basin that's going across the highway or going across the road and tie in my underdrain. I have a lot of flexibility. So you do need 2 feet of fall. If you have ditches that are really flat and no structures anywhere, you might not be able to outlet your under drain, and then my presentation title was false, and I apologize to you. But for everyone who has a catch basin somewhere, everyone who's got a pipe, you can fit your bioretention cell in that ditch and outlet it there. All right, so these fit. The engineering is not that complicated. There's not that much math. They fit. But they're easy to screw up. So let's talk about how to keep it working. So these are common sense things that we've written into our requirements in Ohio that we would like you to steal if you want to look at. Or, I mean, there's lots of DOTs have different requirements. But this is what we're doing. So generally, we're going to talk about how to not clog it during construction, and then when you accidentally clog it, how to unclog it after construction, and then how to try not to clog it after construction with pretreatment, and then put in observation wells so you can figure out where you accidentally clogged it, right? So this is you're going to clog it. You're going to accidentally put construction sediment in your BMP. So saying like, let's put a tarp over it and hope it's going to work, just assume it's going to get clogged and we'll just move forward. So we're going to go through the things that we do during construction that we have written into our notes, and they're mostly photos, so they'll be fine. So the first thing is when you dig out your trench for your linear bioretention cell, just go ahead and scarify the bottom so you can hopefully take advantage of some of that in situ infiltration. You can see in this one it's mostly clay soil, so we're getting almost nothing. I think our estimated saturated hydraulic conductivity at that would be like 0.02, 0.01 inches per hour. So we're not counting on that at all. But go ahead and go the extra step. If you got the equipment out there, scrape it down once. Don't use filter fabric. We don't recommend filter fabric. You can use it on the sides if you have a real good reason, but we don't recommend it. Use these, we recommend 57s and 78s, pea gravel, and then clean sand, and then your bioretention media. So when we put filter fabric across to hold your bioretention media in place, that's where it's going to clog. And when you wrap your under drain in filter fabric, geotextile fabric, that's where it's going to clog. Here, if sediment gets in through our bioretention soil and down, it's going to go to the bottom of those 57s and going to have to fill up that whole trench, 3 inches or 6 inches before it actually causes a failure. So we acknowledge that some of the fines are going to get through, and we don't want to give them a place to cause us problems. So no filter fabric. And when you're using sand, remember, we're trying to get sediment out, so it would be great if you could get clean sand from the contractor, double wash sand, which they can give you. You might have to pay a little extra, but it's why we have BMPs to get the sediment out. So don't let them give you 10% fines in your sand to try to get rid of those same 10%. So that's kind of straightforward. This is one of our pictures. It shows the layers. I like this picture better. We almost never get these pictures where you actually put it in because they had to go back and dig. But you can see where our 30 inches of bioretention mix is, our 3 inches of sand, our 3 inches of 78s, and our 12 inches of 57. So no filter fabric. They work great. These have been in the field for a while. They're looking great. So that's our first thing. Don't use filter fabric. Use clean materials. When you're putting in the bioretention soil, we recommend putting it in lifts and watering it to compact it. So contractors want to put it in a dump truck and drive some piece of equipment on it. We don't want to compact our bioretention cells. They're fragile that way. So it's not that complicated, but put in a lift of 12 or 18 inches, water, and put in another lift of 12 or 18 inches, water. That's pretty straightforward. This is a big one that is not that complicated, but contractors will complain about because it is extra work. But we don't want you to spoil the hole you just dug at the trench right next to that where you're trying to get out of. So you got to take it to a truck or get it off-site somehow or behind a silt fence. Don't put it right next to the big hole you dug because then it's coming right back into the hole you dug. So that's big for keeping the sediment out, is spoiling off-site or into a truck, like you can see there. The other thing that we have good luck with is two things that are helpful. The first one's almost impossible. The other one's not as impossible. So we recommend, if at all possible, stabilizing the site before you dig the hole. So having grass there before you dig the hole, which is a pain, right? Contractor wants to dig all their holes at the same time, fill in all their holes at the same time. So you can work around it. You can talk with your contractor, say, okay, you can do this now, but we're going to have to make sure to go clean this up afterwards. In this example, we were able to keep some grass there, and when we came back and started bringing in the aggregate and the soil, we used that conveyor belt, right, to bring it out from the road, and the contractor would rather be working on the road. He doesn't want to be down in the dirt and the mud, and it was really a great way to bring all our materials in and keep the surrounding ground pretty clean. Or you can try the silt fence way, like other people try, and hope it works. It did work well in this situation on another bioretention cell. Just be prepared that if you're sending construction sediment in there, someone's going to have to go clean it out. So whether or not you do it where you have grass there for some pretreatment or the silt fence, you're going to have to deal with that afterwards. So those are the things we do during construction. Scrape the bottom, don't use filter fabric, use clean sands, don't compact during installation, spray it with water during lifts, and keep the construction sediment out somehow the best you can. Okay, have some plan for that. All right, so that's during construction. And then, okay, so then you got to unclog it after construction. So I just want to show you what this looks like, and this is going to happen. You're going to have this. This is the reason my presentation is 120 megs. Ooh, there's volume. Hope I didn't accidentally talk during this video. All right, so what happened here was it had rained 3 days ago. There was a big puddle. I took a garden rake and scraped it and then got out my camera and took a picture. And it goes down right away, right? So the water goes down right away, which is great. So basically what I'm showing is it didn't take, I know I'm out there with a garden rake and we're not having contractors go out with garden rakes, and that's fine. But when the construction sediment does get in, it clogs that top few inches, which we all know, and it's not that hard to get that out of there. And if you go ahead and plan for that in your notes saying, okay, do this, just like I said, keep it clean, and then when you screwed up, make sure you go cut off the top 3 inches, and you really only need the top 1 inch, and bring back in another small lift of this bioretention soil. It's a pretty easy fix, all things considered, as opposed to letting the contractor off the site like that, and then you basically have a plastic tarp over your bioretention cell that's not going to let any water down. So that's it. That's my recommendation. After construction, have a plan to go back there and scrape the top, which is not wildly expensive. You can go sling out a little more of your bioretention soil. And then after construction, pretreatment. So I want to highlight the importance of pretreatment. It's kind of hard to see here, but in this section, there's good grass along our bioretention cell, and we don't have any plants growing in the bioretention cell yet. You can kind of see from the close-up that soil looks gritty. And gritty is good. That means it's sandy, and it looks like water's going to go down. This section, where they were doing some construction, you can see all the fines washed off of that part of the slope and came into our bioretention cell, right? So you can see how that dirt, that part of the bioretention cell looks a lot different. You got that light brown, at least in Ohio, our construction sediment's always lighter brown than the good stuff we want, the darker stuff. And you can see the film is obvious right there, right? So that's an obvious thing for bioretention cells. And that's the reason we have pretreatment, that's the reason we scraped it. But with pretreatments, you can really prevent just that little bit of fines from coming in and messing up your system. And then we recommend having observation ports. So that's what an observation port looks like in the field. We keep them, if we're in the clear zone, we got to keep them less than 4 inches, which is another safety thing because we can't have more than the 4-inch obstruction within the clear zone. But you can do that, and then they won't get mowed over, which is another benefit, or they'll get mowed over and not broken. But you look down there and you can see it's basically a solid pipe down to that perforated pipe, and I can see then where the water level is, okay, which is real helpful for me to know if I see water on top of the bioretention cell and I open up that well and I see that empty down to the bottom, I know I'm clogged at the top, which is a good problem. That's a problem you want because you can scrape that and fix that. If I see water up there and I see that pipe filled to the bottom, I know I got water all the way backed up, which is a bad problem, which means I got to excavate something down and fix the whole thing. So that observation well is, an extra $40 that lets you know when you have a problem. It keeps people from freaking out when your thing fails, right? Because it's going to fail, you're going to have to fix it, and then your observation well hopefully tells you it's a cheap, easy fix versus a annoying, hard fix. All right, then I'm going to talk about maintenance, and then I'm almost finished. So maintenance is the other question people have. How hard are these things to maintain? So we're not doing any mulch, we're not doing any fancy flowers, we're going to try some pollinators later, but that's really an experiment. We're letting regular roadside grass or weeds come in, and they're working great. The grass is breaking up the soil, the sediment that's coming in, and they're doing great. The one annoying thing about maintenance is you got to try to keep heavy equipment out, and we like mowing with heavy equipment. We've actually had some tractors drive into our bioretention cells, and they're not really that screwed up. And these linear applications, we got 100 or 200 feet of them. If you screw up this 5 feet, of this 200 feet, you're still fine. So you're not screwing up the whole thing unless you constantly drive your wheels right down the middle. Plus, as soon as that tractor drives in and their wheels sinks 18 inches, they'll try to get out. We recommend keeping the tractor tires out and using the bat wing. But even if you get in, we're finding it's not the end of the world. And if you have that pretreatment, we don't think you'll be in there scraping that bioretention cell to regenerate capacity. much more frequently than every 10 years. We don't know. Our oldest one is like 2 years old. But we don't think it's going to be that often, and they're not getting even close. So ready for questions, and I'm sure there's not time. Also, if you want this presentation, let me know. We have a bunch of extra material, all of our notes and plan sections, so you can steal all kinds of CAD and notes from our L&D or from me directly. So, any questions?
Help me thank Jon, and you are correct. There's no time for questions.